Hello, guys. Thanks for coming out here. Thanks, Calvin. I did try to make the title, and in fact, I wanted to somehow fit in serverless in it, but I just couldn't think of a good way. Yeah. By the way, my name is Ananth Iyer. A little bit about myself: I'm an electrical engineer from background. I've done audio signal processing, speech recognition, and a little bit of natural language processing as well. I currently work at Lifomic. Lifomic is a platform that we are building for statisticians, doctors, researchers of hospitals and other healthcare in the healthcare industry. They can leverage our platform to aggregate their patient data from clinical data to genetic data to their wearable devices. All those things comes into one platform, and obviously, we have built with analytics and machine learning as our front end in terms like we want to think about people using analytics on this data. So yeah, again, in terms of people showing interest in Lifomic, I'll be glad to talk to them. If anybody is interested to work for us, I'd like to talk further. All right. In terms of fake news, I don't think I need to introduce fake news much. It has tremendous effect in our current environment. And I thought this graphic kind of pictures it out very nicely. I found it on another blog post, and I shamelessly took it. But all right, what are we going to talk about today? So I'd like to introduce the whole thing about NLP and how simple they've made it these days. While you guys get a laugh out of the graphic, I'd like to, yeah. That's like the thing that I really liked about the second graphic was they went ahead and said it's an original picture too. It's they made sure it's validated. In any case, so just to make it how simple it is to get started is what I would like to demonstrate today. There's lots of theory and research and computation happening in the background, but if you just want to build up a system, I'm going to show you how this can be done. I did this in a matter of a couple of evenings, and I'm not an expert in AWS. I'm not an expert in natural language processing as well. But just to get going, it's rather straightforward. And all of this happens mainly because of this concept of pre-trained models that large companies and other individuals are actually putting it out. In 2017 and 2018, this was a big thing in images. You might have heard of ResNet, YOLO, MobileNet, a variety of these models came up. So the main idea is, a large company or a large organization which has great resources, they go ahead and build this model using a really large data set. And that model is usually open sourced. So if I want to build a model, what I would do is I would take that generic or world knowledge based off of that model, and I'm going to fine tune it. And that's what lets us get something which does very well in a much sooner and a quicker way. So we'll talk about how we can build a classifier and an inference model as well. And then finally, the little bit of the AWS that comes into this talk will be how to package it and kind of deploy it on Fargate. So at the end of the day, it is serverless because I'm going to use Fargate for it. I'm not managing any servers. So let's see how we do it. All right. For any basic machine learning problem, I think my requirements, my prerequisites are pretty much these four things. You need a data set that represents your problem domain. You need something to say that, hey, this may not be extremely large, but you need a significant size. Something in the order of thousands of rows, in my case, is more than sufficient. So when I say data set, typically we look for something which is labeled. So you need the data and the ground truth of what it means. So in my case, it's just going to be a bunch of sentences, each of them labeled as whether it was a fake statement or a real statement. So pre-trained model, and then we need some compute, because many a times this training is extremely intensive. You may need a GPU, you may need a cluster, you may need a Spark, Hadoop type of an environment, but you do need, you need to keep that in the back of your mind. Your laptops might not be enough most of the time. And finally, to do inferences, preferably a hosted environment to do that. So as my choices, I picked PolitiFact. This is actually a website where humans look at statements, either it's coming from Twitter or Facebook, from most of the famous personalities, and humans actually go ahead and label it in a scale of 6, I believe, saying from, this is a true statement, it's mostly true, mostly false, false, and finally the last one is the best one, is called pants on fire. So it's a lie. And then second one is Bert. Bert is a system which was open sourced. It's a model. It's an architecture developed by Google. It's brand new. It was a paper published in November 2018, just a few months before. I'm going to talk a little more about it, and then I just picked the cheapest GPU instance for my training, and then I used Fargate to host my inference or my model. All right. So the early 2017, I believe, this paper came out, liar, liar, pants on fire. This was a benchmark data set they made for fake news. It's based off of PolitiFact. So they've kind of made it structured so you can use it nicely in most of our algorithms. Yeah, that's what I picked. It's very structured. I can just go ahead and use it. Nothing much to talk about it. And then I picked Bert. Bert, it's another funny thing, when I was doing this slides, my son comes up, and after looking at this, he's pretty much convinced that my work is on Sesame Street somewhere, because as you'll see, BERT actually stands for bidirectional encoder representations for transformers. I have a feeling, or pretty much many of them have a feeling, that BERT was an acronym they made up, and they expanded it out just for the name, because earlier to BERT was another system they came up that was called Elmo. You know where my son is getting that ideas from, right? Anyway, all of these fall into the same category of pre-trained models. So there's a lot of theory behind this. Clearly, I won't be able to go through what exactly the BERT architecture is. But just to give you a brief high-level view, it's a really large neural net at the end of the day. There are several things that have been developed over the past year, like attention mechanisms, input codings, what have you. At the end of the day, if you look at this diagram, there are 3 systems, actually. I just picked this graphic from their paper. Elmo, and then there was an open architecture, and then finally BERT was Google's. So what you see, the similarity here is the inputs and outputs. That's what we care about. The inputs, the E1, E2, EIs, are just word tokens. You take a sentence, split it up into words, and then that's your input. These are usually, it can be about 30,000. Your vocabulary could be a size of 30,000. But the bottommost layer is basically the number of words that are going into your classification algorithm or a summarization algorithm or what have you. And on the top, the T's are the targets. So if you wanted to classify each word to represent something, you could do that. If you want to take this entire sentence and classify it as fake or no fake, or positive or negative sentiment, what have you, that fits in this. So at the end of the day, each of those units you see are actually networks. So these are really deep networks. And the model that was actually trained and given out is around 400 megs and I think 3 million parameters in it. So it can capture a lot of meaning and semantics from the data that you're learning. So this is not new, as I said. Having pre-trained models and input mappings to output is not new. But the neat thing that comes out of BERT is the way they actually trained it. So the way they trained it, all of that I spoke about, you're trying to get a representation of the language. So whether it's English or Chinese or what have you, any language, you just need a model or a world knowledge for that language. So the way they trained it was, they had 2 tasks. They let the neural network learn and solve 2 tasks. And this was all done in a completely unsupervised way. You don't have to go through any data. You don't have to look at, label any data. That's the beauty. So the first task they did was, given a pair of sentences, do they follow each other? Is the second the next one? So they created a whole ton of data. The first example here is the two words is a sequence. It forms a paragraph. The second one, these are two unrelated. And the network is supposed to learn whether the two are related or not related. So this gives a sense for looking across the semantics or looking across the sentences. And the second task they so this was learned simultaneously. The second task they did was, given this sentence, can I mask out some of the words and let the neural net predict which word will fit best? Which is the missing word? Can I predict the missing word? And they did it with some kind of scheme where they masked out only a portion of it. 10% of them were masked out. And then the other 10%, they randomly replaced it with another word just to add confusion. And then finally, the other 80% they didn't touch. Or rather, I mixed up the order, but the other way. So to do this, they needed data. So the data they picked from their library, what they mention is basically two corpuses. One is the book corpus, and the other one is the entire English Wikipedia. So I'd like to show you the magnitude of data that has been used to build this word knowledge. So it's 2,500 million words, 2.5 billion words, plus another 8 million words added into it. So you get a good representation of English if you learn this. And this has shown to exceed performance in many tasks for now, like question and answering, classification, what have you. All the benchmarks was blown away. But obviously, in the past few months, things have evolved further, and it's gotten even better. But anyway, what I want to highlight is we don't have the scale. I don't have the GPU scale to train anything in this magnitude. I would be broke. And Google used their TPU instances, which is, I don't know, they used an array of 16 TPU instances, I believe, and it took them 4 continuous days. So it's a really big, large magnitude, and it's something not an individual can probably handle. You need a team for it. But the good thing is you can use this to build your own system, so that the model has been outsourced and you can use it. All right, moving on, then the next piece in my puzzle was Fargate. I'm not an expert in AWS or Fargate in any manner, but I would like to show and say that why it fit in my solution very well. Because this is also, again, taken up by AWS's initial infographic. So I know how to use Docker. I know how to build a container. But I don't know how to go and manage the servers and all that stuff. And clearly, based off this, Fargate does that for me. And that's exactly what I wanted. And I picked it, and I learned it was super simple. So I'll just show you how I did it as well. So it was very straightforward. So choice of Fargate was natural for me because I think even the last talk was about Lambda. And Lambda would have been something that I could have used. But showing the magnitude, the Docker file I have built is in the order of 3 gigs, and it clearly would not fit the 50 MB limitation of a Lambda. So, all right. Now a little bit about the actual details and why I think and why I have been saying the word simple so many times. So I used PiTorch. Initial implementation of Bert was in TensorFlow, but still PiTorch. And this library is an elegant library that people from Hugging Face have put out. So it can load the pre-trained models from Google. But I just chose this because of the elegance, the way they have built it, and it's so easy. It may be hard to read the actual code out there, but the thing that I want to highlight is there is already a Bert pre-trained model class that is in this function, rather in this module. And to do your own custom classifier, all you need to do is extend it, and you need to add a function called forward, and do what are the operations you want to do beyond that. So here you can see the line here. The self.Bert is actually the Bert model. So I'm extending the Bert model to add a classifier. An NN linear is basically a simple linear layer on top of the Bert's architecture. and I'm just tweaking the model to get what I want. So you can imagine you can add anything out there. It doesn't have to be a linear layer. You can add another huge network on top of it. You can add something that can do question and answering. That's exactly where this shines a lot. And in my case, a linear layer and 2 classes. I'm looking for either it's fake or not fake. That is sufficient. And finally, the softmax is the way that I can get a probability value between 0 and 1. So all I had to do is these 20 lines of code, 27 lines of code, to get something to get started. So obviously, there is some other infrastructure around it. You need to run a loop, read the data. You need to parse the data, but things like pandas and all is very convenient. So you just take this class, run this in a loop, and then it just trains itself, pretty much. And then to actually do the inference, I use the class that I built before, Bert sequence classification softmax. And now I can load any model, the model that I just built. And finally, I can just call the function with the input, the new input text I can get. So I needed a tokenization step as well, because you just get raw text. You need to break it up into tokens. And then pass it into your model, and finally you get the probabilities for each class. And as you can see here on line 17, all I'm doing is taking the max. Which one has the highest probability? Just return that as the class that I've identified. And I just give it the label true or fake, and I just return that out of this class. So again, as you can see, just about another 20 lines of code for inference. So from this, next step was to see how I can package this off. So I, keeping in the spirit of keeping things simple, I just used a Flask wrapper around it. I just have a global fake detector that I have just created, loaded up the model, and then as an input, I get a JSON string with text, pass it into that function, return it. That's about it. Can't get simpler than this. And this is how my Docker file looked for packaging it up for before sending it into Fargate. So as you can see, I just copy over my module, my code into it. I created a Conda environment. I installed Bert pre-trained into it, and then just launched the server. That's about it. And all right, and then the next step for me was to actually see how I can use Fargate. So the first thing that I learned, so this was an exploration and something that I learned over the past few weeks. So after I built the Docker locally, I had to tag it and push it to ECS. I think it's probably common knowledge to many of you here, but it was new to me and it was good stuff to learn. So the pushing took a while because my container was about 3 gigs in size. With all the Python modules, the actual model itself, and all of that put in place. But at the end of the day, that went well. And then to actually use Fargate, I didn't do any scripting. I just used the console to do it, but I'm sure there's much nicer, smarter way to do it through some kind of continuous integration framework, I would assume, to achieve these things. But all you need to do to get this up and running is to, you have to set up a cluster and a task definition. And interestingly enough, AWS has made it so simple. There was a wizard that just took me through the steps. All I had to do was give it the link to my registry for where my Docker has been stored, and select how much memory and what kind of CPU I need, whether I need a GPU or not. And then, it just went ahead and did its stuff. And then after 10 minutes or so, it said, I built these 10 things for me. So I chose to build, have a load balancer also in front of it, so that I can hook up my Route 53 easily. And after these 10 steps or so, it took 10 minutes. So I'm not doing a live demo because it's very time-consuming. But once this was done, I think I was up and going. I did a little bit more decoration. I connected my Route 52 to this ELB, and then that's it. So I just want to show you what came out of it. So here I have a bunch of examples that I picked from yesterday's PolitiFact, like the actual new stuff. So to do training, I had about 10,000 examples, which was picked sometime in the last year. So yesterday I just went through and I clearly picked sentences that they have marked as pants on fire and which are completely true. The ones that were in the middle, I kind of said it may get confusing. So if you, I hope you can read, but it's basically the first few are all fake statements. So just send a request. This is actually now live. I have my fake.aniyer.net. That's where I have it hosted now. So it comes back as fake and got a confidence of 0.54. So it may not be as fake as, but still it classified it as fake. So just going down the list, pretty much some of these are obvious that it is fake. But these are news, so all of these just come back as fake. So now just going back to the new one, on the true side, so it's just flipped to true, and it has a good enough confidence. So all of them came out the way I expected it to be honest. But I was able to find some clearly wrong examples where it did mistakes. And it's very tricky. I mean, if you look at the actual data, the difference between fake and not fake is very subtle. It's actually, it's not easy as a human to also figure out. You need other sources. So I ran through the system. I actually looked at the benchmark is around 60%. So it's a two-class classifier. So 60% is just a little better than random guessing. So it's not a good system. So that's the benchmark. And when I tried this out, I was able to get around 64% with this. I think we can get a little better still because I didn't run as many iterations through. It takes a long time, and I didn't want to spend too much money on my GPU instances, so I did 3 iterations, and I said I'm going to stop it now. But many a times you may have to do a couple of hundred. I think sometimes a couple of hundred is necessary for a task, which is very difficult. That's one thing. The data itself, as I said, is very ambiguous, so it may be the problem itself is inherently unsolvable. And that's why PolitiFact actually need humans to go through it. And the other thing is, keep in mind, all I'm looking at to do this classification is this piece of string. Maybe even if I add the author to bias it a little bit, you will get more accuracy. People have histories of doing the same mistakes. And then maybe we can add locations, the source, whether it's coming from CNN, Fox, or what have you. All those things could help. So currently, looking at just the text, I think this is best we can do for now, apart from adding more compute cycles for training and all that stuff. So that seemed like a reasonable success for me, because at least on the ones that I picked, the first 10 I picked, all of them worked fine. On the benchmark itself, it gave me 64%, but here it gave pretty nicely. So the other thing that I could do is, I told you about the 6 granularity of fakeness that they have. You could potentially extend your classifier to do the 6th level classification and see if that does any better. But if you guys want to put any phrases, I will be glad to. But if that's not the case, that's all I had to share with you guys today. If you want to talk further, have any questions, comments, I'll be glad to.
I'll give you the microphone if you got questions.
On your last example, what was the .rest file? What is that thing that you were using for that?
Oh, you don't know about that? Come on, man. Oh. So this is just Visual Studio Code, and if you have a plugin called REST Client, this actually you just say post, and you can give it your endpoint, and you can give it all the headers right here. You can give it all your body here, and then just send request. The right panel gives you the response. Like a quick and easy Postman if you don't want to go. And you can have it checked in. Yeah, it's very sweet. Yeah.
If anybody's got questions, I'll bring the mic over to you so that way we can get them on the recording. I had a quick question for you on this.
Yeah.
So when you're running your actual tester, you don't need like a GPU instance to do that, correct? I mean,
No.
You could run that on a Raspberry Pi once you've got the model pre-calculated.
Yeah, I would think so. Yeah, I don't think. I mean, I don't have GPU also on the Fargate, and considering the size, I mean, the response I'm getting is in like 300 milliseconds. I don't think so. I mean, it's large. If you start doing lots of parallel requests, most likely you may need GPUs and stuff, or somehow to handle the parallel. But I don't think so. I mean, the inference part is usually the cheaper.
Mm-hmm.
The training one is the most expensive one. So that's why I needed the GPU instance for training.
Okay.
I think I would add on that is that if you were trying to train as you're processing to see where you're missing, then you would have to figure out some way to pipe that off of there somehow. But
Yeah.
But yeah, I agree with you that you don't need the GPU for that. So, did the training set here that you used, these look like they're all headlines more than full body text?
Yeah.
Is that what the training set was as
Yes.
well?
Yeah.
Okay.
It was kind of short statements,
Yeah,
either
yeah.
Twitter statements or headlines.